The next thing is Fischer-Carnot harmonic decomposition AO estimate. So the Fischer-Carnot harmonic decomposition AO estimate is named after the Russian mathematician who derived this minimum mean square approach. So the goal is to minimize the mean square error of the array output under the constraint that the norm of the weight vector be equal to unity. So here there are two goals involving mainly. The first thing is the mean square error of the array output under the constraint. We have to minimize that value. And the second thing is the weight vector be equal to unity. So the eigenvector that minimizes the mean square error corresponded to smallest eigenvalue. For an m is equal to 6 element array with two arriving signals, there will be two eigenvectors associated with the signal and the four eigenvectors associated with the noise. So the corresponding pseudo spectrum is given by 1 divided by Hermitian of theta e1 vector, the modulus of square. So here this E1 is nothing but eigenvector is associated with the smallest eigenvalue lambda 1. So now for this Fischer-Carnot harmonic decomposition spectrum. So this is the spectrum for the theta 1 up to theta 2. So here this is the spectrum. So it is mainly we are using to minimize the mean square error and the array output, and also we have to make the weight vector to be unity. So now this is a harmonic decomposition. So we can compare the previous spectrum of the linear prediction estimation. So see here this is that peak type of curve, and here we are using that single decomposition D spectrum. So now see here, the first thing is we are going to do this Cartesian basis vector in that this linear prediction AO estimation. So here we need to find this thing is very simple thing only, the 1 divided by A Hermitian of theta, that is eigenvector 1 the whole square. Thank you.